My name is Odd Gurvin. I'm a project manager at the Norwegian Cognitive Center. Today we're gonna get an introduction to deep learning from Dr. Yong Yu, who is a senior researcher at Norwegian Research Center, as we also like to call NORS. Our value proposition is we are enabling your competitive advantage. What we do is to try to help each company to get competitive advantage using AI. We have a lot of services for you. It's all from, you can use IBM Watson in the project. We have AI expertise available for you. We have a learning arena like this. We also help organization with public funding. We have guidelines and regarding governance and use of AI. We have an AI lab ready for you to use, and we have two different startup programs, one by Nora and one by IBM. We also have students, matching students with projects and projects with students, and we also have two different projects that are costing something. The rest is free. What we do is we have inspiration and learning activities like this. We also have some Discover Garage where we can explore different kinds of AI and identify use cases. And we also have an offer for those who have come a bit further. They know what they're going to make, but they don't have the capability or capacity to do it. And we try to help each company to achieve the goals they have within AI. And we have a lot of events. The next event is already next week, where PwC is going to tell us a bit about how to succeed with implementing AI in the organization. I will end the presentation now and introduce to you Yong Yu at NORS. Welcome, Yong. Could you please present yourself first, what you are working with and the organization you work in?
Yes, thank you, Wood. Okay, good morning, everyone. Welcome to this presentation. I will give a very general introduction about deep learning and different models. My name is Yong Yu. I'm a senior researcher at Norwegian Research Center, NORS. NORS is one of the largest research institutes in Norway. So in this talk, we're gonna generally introduce deep learning, and then we will briefly talk about different deep learning models. For example, convolution neural networks, that is mainly used in computer vision, and for time series analysis, recurrent neural networks are often used, and also it's a transformer that can be used in both computer vision and time series analysis. And finally, we're going to introduce a general pipeline of applying machine learning in practical problems. So due to a time limit, I won't go into very details about models, but if you have any questions, please just ask. So first of all, let's talk about some concept. People often say AI, machine learning, deep learning, but are they the same thing? According to the concept, some definitions from Wikipedia, AI, artificial intelligence, is defined as intelligence demonstrated by machines So AI is a very broad concept. It covers a lot of things. And if we said AI contains two main parts, an hardware part and software part, then machine learning is the study of computer algorithms that improve automatically through experience and by the use of data. So machine learning is mainly doing the software part. And it's computer algorithms, and it has to be trained and learned some knowledge by the use of data. And deep learning is a part of the broad family of machine learning methods based on artificial neural networks with representation learning. I will explain representation learning later, but according to a definition, deep learning is based on artificial neural networks. So according to the definitions, we know that deep learning is a part of machine learning, and machine learning is part of AI. And actually in this talk, we'll mainly cover only a small part, but probably the most successful part of machine learning, which is deep learning for supervised learning. So then deep learning is based on artificial neural networks. So, but what is artificial neural network? Let's start with a simple example. If we want to predict a price of the house, so a house price can probably be determined by several factors like size of the house, the age, how many rooms, and the area where the house is. So maybe we could use a simple linear combination of the different factors to predict the price of the house, like this one. And maybe we also want to predict the energy level of the house. So we could use another linear transform to derive the energy level from same factors. But of course, the house price and the energy level can be determined by many other factors. But here, we just assume that they can be predicted based on these four factors. And maybe we also want to decide or predict our willing of buying the house or not. For example, based on price, based on energy level. So we could probably use another linear transform to derive the willing of buying. So the linear coefficient in the linear transforms can be found out using some optimization algorithm. And actually, from that example of willing buying a house, we already built neural networks like this. So this is a typical artificial neural network. And it mainly contains three layers: the input layer, an output layer, and the hidden layer. In the example of buying a house or the price and energy, we know what the middle layer is for. But in practice, we do not directly see the result in the middle layer. So this is the reason why it's called hidden layer, because the information produced from this layer is hidden. But we can see our input, and we could also see the final output. So this architecture is called multi-layer perceptron. And if we take only one of the nodes in the hidden layer, that is actually inspired by neuron, which is a perceptive mechanism in our brain. So in our brain, there are a lot of neurons. And each neuron, it takes some stimuli from like an axon from another neuron, and several axons from different neurons. And then some operations can be run in the neuron. And then it will generate another axon, an output axon. So the operation can be represented by a linear transform like what we have done in the example. But there's a very important mechanism, or we call it activation function. Why do we need that? So if we still use this example of William buy a house, if William buy a house is a linear transform of price and energy, and the price and energy are also a linear transform based on these different input factors. So according to a chain ruler of linear transform, then we know that the William buying a house can also be determined by a linear transform of size, edge, rooms, and errors. But in real world, most problems are nonlinear. So we couldn't use a linear transform to represent a lot of problems. So that is the activation function is introduced in order to make the transform nonlinear. So there are different activation functions. Linear function is one of them that is widely used in regression problems in which a single value is often derived. And there are many other nonlinear activation functions. For example, ReLU, standing for rectified linear unit. And ReLU is widely used in different models. And people often say that if you do not know which activation function should be used, then just use ReLU. And TAG, this shape and the formulated in this way. TAG is often used in recurrent neural networks, and sigmoid that is often used in binary classification, and softmax is often used in multi-class classification. And GALU, Gaussian arrow linear unit, that is proposed in transformer model. So then we know what artificial neural network is, and let's talk about deep neural network. As we have said, that artificial neural networks often have only one hidden layer, but we could also use more hidden layers between the input and output. For example, in this one, then artificial neural network will become deep neural networks. So that means deep neural network is just an artificial neural network with more than one hidden layers. That is deep neural network. And in artificial neural networks or deep neural networks, we could use a linear transform in each neuron, but we could also use other operations. For example, convolution. So then a deep neural network will become a convolution neural network that will be introduced later. Then we could also define deep learning as to use deep neural networks to do machine learning. So then are neural networks really useful? Then this is related to that in real world, most of problems can be formulated as solving a mapping function between input space and output space. The space can be Euclidean space or can be Hilbert space or whatever space. So we want to find a mapping function f. So imagine that, for example, if we want to do an image recognition, that means we want to map from an image space that could be a 2D space or 3D space to another space, which can be just a scalar indicator what category this image is. And you can imagine that most of the problem can be formulated as this, as to find a mapping function. So according to a so-called universal approximation theorem, neural networks can represent a wide variety of interesting functions given appropriate weights can be found for the neural networks. However, in practice, these appropriate weights are often very hard to be found, especially in a very high dimension space, because neural networks often have, especially deep neural networks, often have a large amount of parameters. So that means the solution space is in a very high dimension. So in this case, it's often very hard to find the appropriate weight in order to represent the problem. Then how to find the appropriate weight, meaning that how to solve neural networks. So this, we often use something called gradient descent. And because the problem of finding appropriate weight is too often that we want to find the mapping function that can simulate the real distribution or real problem. So that means we want the distance between the predicted result and the real result as small as possible. So in this case, we often define a loss function. The loss function is to represent the distance. The loss functions can be very different in different scenarios. For example, for a linear regression, we might just use the absolute error or use the square root error. For classifications, we could use cross entropy and so on. And we know that a loss function, because the loss function is a function of different variables indicating different parameters in the model. So we know that the loss function will change at the fastest speed along the gradient descent. So in this case, we could use gradient descent to repeat the update of the weight based on the gradient until we reach the minimum point of the loss function. And in practice, we often use stochastic gradient descent, SDG. That is to simply to update the weight at each iteration on the randomly chosen subset of your training samples. And for each update, we use the parameter alpha to control the step to update weight. This alpha in machine learning is also called learning rate. It controls the steps of how much the update should be. And so this is a very important parameter, but this parameter cannot be learned from the training process. So this kind of parameter is called a hyperparameter, and that we need to define ourselves. And for finding the appropriate weight in the deep neural network, because there are a lot of layers. So in order to handle this, we often use a chain ruler in the back propagation for the weight update. That means we calculate the gradient from the last layer up to the beginning layer, one by one. And then why do people want to use deep neural networks? There are several reasons. The first is depth really matters. So for example, if let's look at pictures here. If we are going to use one layer with 9 neurons, so in principle, this architecture can represent 9 different patterns. However, if we stack these 9 neurons in 3 layers, and this architecture can actually represent 27 patterns. So in other words, we could use the same parameter or same number of neurons to represent more complex patterns. So that also means if we use a deep architecture, we could represent a very complex problem. And another thing is related to what does deep neural network learn? And this, if you know something about traditional machine learning, because in traditional machine learning, people often spend much effort on the feature engineering to design manually some very sophisticated features, and then use some other machine learning models like artificial neural networks, like support vector machines, sorry, for the problem. But with deep learning, with a deep architecture, for example, in this case, we want to recognize who is this picture is. So we just give the model with raw input, which is image, and then we can get final output, recognition of the image. And in the middle layers, we actually can get edges in the maybe in the earlier layer, an object part in the middle layer, and object models in the later layer. So that means deep neural network can learn representative features itself without needing feature engineering. That is why also we called deep learning as a representation learning, meaning that the model learns representative features itself. So that makes it possible to develop an end-to-end approach. We just give the model a raw input, and the model will tell us the final output without other things. So that is very convenient, isn't it? And the third reason is that scale really matters. According to the principle of deep learning, you see that it's actually quite simple. And so because the principle is very simple, why wasn't it be invented in the past? Not because of scale. As we know that a deep learning model often has huge amount of parameters. In order to well-train a huge amount of parameters, we often need huge amount of data. We often need a powerful machine, a GPU, TPU, or computer clusters. So in the past, we don't have this. And only nowadays, there are really a lot of data, for example, images, video, and document, and text information. With this huge amount of data, with the powerful GPU, we could train a deep model with huge amount of parameters. Then this model will have very powerful representative capability. So data matters, scale matters. And also because nowadays we have a lot of data, like on images, on text. This also was the reason why deep learning has been most successful in the two main areas, computer vision and natural language processing, because we have a lot of data in these two types of problems. And now let's talk about deep learning for computer vision. The many used model is called convolution neural networks. So assume we have an image, and the image resolution is sovereign by sovereign, and each pixel has 3 channels. For example, if we want to classify this or recognize this image, and in the past, we're going to just, we want, in the traditional machine learning, we want to derive some representative features like edges, like color, brightness, object, or whatever, and then use some traditional machine learning models to recognize the image. But with deep learning, we want to develop an end-to-end approach. We don't want a sophisticated feature engineering because I don't have that time. So, however, if we use a raw image like this, 1000 by 1000 by 3, that means we have 3 million values as input. And let's assume in the first layer, we use 256 nodes. That means only for the first layer, we will have over 70 million parameters only for the first layer. So this is very hard for a computer to afford, especially if we want to build a deep architecture, then there will be really a lot of huge amount of parameters that no computers can handled. Fortunately, images have some interesting or particular characteristics. For example, it has a local representation, and the pixels in the local region are often similar to each other, and also images that often have a similarity on pattern representation across image patches. For example, if we look at different image patches on this image, like this patch of sky and this patch of trees, even these two image patches look quite different from each other, but actually we can use the same pattern to represent them. The pattern is like a texture. So this patch has a smooth texture, and this patch has some regular texture. So that means we could make use of this kind of similarity. So we use the same kernel for different image patches, and in order to share this kernel, to share the parameters because of the similarity. And widely used kernel is convolution. Convolution is like this. We just slide a convolution kernel across over image pixels and to calculate the output from a convolution operation. And relevant image features can be extracted by convolution. This is because our human vision system is often sensitive to change, like the pixel change that is edge, like movement, that's also a change. So we could use convolution to capture these features. And maybe you ask, can we also use other transform? Yes, the answer is yes. If you know something about image compression, then in image compression, cosine transform and wavelet transform are widely used. But the main reason is why the convolution is widely used is that you know that convolution is just it's very simple. It's just an operation of dot product and summation. So it's very easy to compute. And then we can use convolution to build a network. So if we are going to use one single layer network, then we use a convolution kernel and slide the kernel on the image at a certain stride, or a stride is a sliding step. For example, if we use a convolution kernel with 3 by 3 by 3, so that means we use this 3 by 3 by 3 matrix sliding on the window, and we use only this convolution kernel for all of the image patches. And then finally, we could get output with some dimension by some dimension. And this dimension nx and ny are actually determined by the original image resolution and the kernel size and the padding method, and also the stride steps. And so, but as you can also see that this convolution kernel also only has 27 parameters. So compared with over 70 million parameters, it's much, much less than that. And any computer can afford such kind of computation resource. And we could also use multiple convolution kernels to capture different features. For example, this convolution kernel might capture the edge in vertical direction, and this kernel might capture edge information in horizontal direction, and so on. So for example, if we're going to use 256 kernels, we're going to get 256 output. each has a resolution of nx by ny. Even though 256 kernels have been used, it's the total number of parameters is still very small. And we could also stack multiple layers, and different kernels can be used in different layers with different kernel size, different number of kernels in order to capture different image features at different scales. Then we have already built a deep convolution neural network. But please note that these weights are all different. I just use the same letters to represent them, but they are actually different, and they are all learned from the training process. And let's talk about some representative convolution neural networks. The first one is called LeNet, which was probably the first one. It was proposed by Yang Lichun. Maybe you have heard about this professor. He's one of the receipt of the Turing Award because of deep learning. And in 1998, he proposed this network for digital recognition. It has two convolution layers. And from a perspective of nowadays, this model is quite simple, but it actually achieved very good performance in digital recognition, and it has been widely used in bank check recognition. And another network is called AlexNet, which is under the name of the first author. It was proposed in 2012. And this was revolutionary work. Why I said that? It's because there has been image recognition competition. In the past, people often used sophisticated image features and followed by, for example, support vector machine or support vector regression for image recognition. But in 2012, Alex and his colleagues proposed this deep neural networks with 5 convolution layers, and they increased the accuracy of image recognition by over 10% against previous years. So since that, deep neural networks have attracted a lot of research interest in computer vision or image recognition area. And even this architecture is not deep, it's quite shallow, only 5 convolution layers. But at that time, in 2012, because the computer power is not that strong yet, and the authors had used a lot of tricks in order to train the model sufficiently. And this later, something called VGG. VGG stands for Visual Geometry Group at University of Oxford. So the feature of VGG is that it tries to employ the application of small convolution kernels. So in VGG network, only the kernel of 3 by 3 convolution kernel have been used. And this is the architecture of VGG 16. It has 16 layers, and it can also be added by 3 actual layers to become VGG 19 model. So this model has demonstrated only the small convolution kernels can also achieve very good performance, given that sufficiently deep architecture has been used. And this also relates to the an interesting topic of receptive field in computer vision, but I won't go into details about that now. And however, a deep neural network often suffer a problem that is vanishing or exploding a gradient issue. This is because when model is very deep, containing a lot of layers, the gradient, when we are doing gradient descent, the gradient can become very small, or on the other hand, very large, such that the model can be very hard to train. Because, for example, if the gradient is very small, then if we're going to use a gradient descent, then if the gradient is close to 0, then the update will be very, very small. So the model will be very hard to be updated. So that limits a deep architecture of neural networks. However, in order to overcome this, the issue of vanishing gradient problem, those very clever researchers have found that it can be simply add a shortcut across different layers. For example, as you can see here, there's a shortcut from this layer to this layer, and another shortcut across this layer and this layer. By simply adding this shortcut, and the model will actually just learn the residue between this layer and this layer. So this kind of architecture is called residue network because the model actually learns the residue. And shorted as ResNet. ResNet efficiently solves the problem of vanishing gradient or exploding gradient problem. And this is also a revolutionary work because the idea of residue network has not only been used in ResNet, it has also been used in many other networks, including transformer. And another problem is that we have talked about in AlexNet, relatively large convolution kernel size have been used, and in VGG, a small kernel size has been used. But what is the most suitable kernel size? It might be hard to answer this question. So in this network, it's called GoogleNet. Some researchers from Google, they proposed to combine different size of convolution kernels together to generate this inception block. It has 3 different kernel size. They just concatenate the different convolution kernel size together and then stack them together to build this GoogleNet. That's also a very interesting idea. If we don't know which one is best, we just put them together. And however, and lately there's another research topic which called neural architecture search. That is because people are often very lazy. I don't want to design the model myself. So maybe is there a way that I can ask my machine to do this job for me? Yes, so then this neural architecture search, NAS, has been invented. That means given the machine target problem, given some searching space, given some searching strategies, then the machine will try to find out what is the best model based on the searching space, based on searching strategy for the target problem. So this is a product from neural architecture search. And the model is called efficient net. It has several different configurations. However, because this is a product from automatic search, so it might be difficult to explain why this model is built in this way. because it's not designed manually. But also that's a very, and this could be a very promising direction because with NAS, people do not need to spend time on designing a very good model. We just ask the model to do that. But NAS often requires very powerful and expensive computing resources. And so the applications of convolution neural networks that can be widely used in different image analysis. For example, image content recognition or object detection. But object detection often involves two problems. One is object recognition, another is object localization. That is to localize or to predict, for example, the coordinate of a bounding box of an object. That involves regression problem. And also image recognition, like the UNet, which has been widely used in medical image segmentation, image generation or super resolution to generate high resolution image based on low resolution ones. And together with other machine learning techniques, convolution neural network can also be used in augmented driving. For example, Tesla uses a lot of computer vision based on convolution neural networks to do augmented driving. And it has been used in computer games like AlphaGo. You might have heard about that, but AlphaGo is mainly driven by something called reinforcement learning. And also together with language processing, CNN can also be used in chatbot and so on. But there's another important information type, which is time series. For example, speech, for example, text. Can we still use convolution neural networks or multi-layer perceptron for time series analysis? The answer is probably yes. People have used 1D convolution neural networks for time series analysis. But there's another more suitable model for time series analysis, which is called recurrent neural network. But since this is a quite long presentation, I would suggest that we take a short break. So let's say 5 minutes. Please grab your coffee, read your emails, and then I'll see you again in 5 minutes, 10 to 10. Yeah. Okay, so welcome back. Maybe we give half minutes or 1 minute for people to come back. Now let's talk about another topic, which is deep learning in time series. The widely used model is called recurrent neural networks, RNN. So let's start with an example of machine translation. For example, if we want to translate a sentence from English into Norwegian, I speak Norwegian. In Norwegian, it could be ja snakker norsk. So I is translated into ja because I is subject, and then we know that it's probably followed by a verb, and then speak is a verb, and in Norwegian it's snakke. And according to a context, so speak is probably followed by language as object. So in the English word, the sentence, we have Norwegian, and in Norwegian, norsk. So then based on the analysis, we could translate I speak Norwegian into ja snakker norsk. So we can see that in this sentence, there's a very strong connection across in different words. Speak follows I, and Norwegian follows speak. So in order to model this very strong connection across in different words, the convolution neural networks might not be very powerful in this sense. For this purpose, people have proposed a recurrent neural network. If we write it like this, we split it out. For example, X is a sequence of data. The sequence means a sequence of data point. For example, I speak in Norwegian. I could be X1, and the speak could be X2, and the Norwegian is X3. So they are at different time steps. And Y is another sequence of time points. Ja snakker norsk, Y1, Y2, and 3. And also, but in some cases, it could be just Y could be derived from last time point on. So we know that because I important, it has some information for speak. So that means we need a way to convert the information from previous timestamp to the next timestamp. So in this case, we use something called the hidden state. So for example, in this one, a node takes input at time point 1, and it runs some transform. This could be just a simple linear transform, and it could produce output, but not necessary. But more importantly, it will generate some information from this time point, and which will be used for the next time point. Let's use my method. Like this H1, that is called hidden state. Hidden state is produced from a previous time point, and it will be used in the next time point. And we repeat it until the final time point. So, but remember that this X1, X2, up to Xt is all, it's actually just input X. So if we draw the picture like this, X, and we have Y, so that means for each step of within X, it will also give some information to itself. So we can use something like this to represent the model. So that is why this architecture is called recurrent neural networks. And also, for each time step, we could use a linear transform followed by an activation function. As we said before, 10H is often used in recurrent neural networks. And please remember, note that the same weights are used for all the different time steps. We could redraw the plot here, and we could also use different weights in order to capture different features for the input X. And of course, we could stack multiple layers in a network. So then in this case, we got deep recurrent neural networks. But please note that in recurrent neural networks, we do not often use very deep architecture. The reason is that time series input can be quite long. So in order to appropriately handle a long time sequence, it's very hard to use a very deep architecture with many layers. So maybe 2 layers or maximum 3 layers are enough for most of the time series problems. And however, the vanilla recurrent neural networks often suffer vanishing or exploding gradient problem. It's still because of time series signals can be long, containing many timestamps. This is the same reason as when convolution neural network is very deep. It also has this vanilla vanishing gradient problem. And also vanilla recurrent neural networks also suffers from long-term dependency problem. For example, if the information in the beginning is very important for the later time point, and this information, because the information need to be conveyed step by step through all the middle time points. So this the early information might be hard to be kept for the later use. So in order to handle the problem, researchers have proposed this something called long short-term memory. This was proposed in the 90s. And in long short-term memory model, it uses a mainline. This mainline will try to convey the important information from the beginning up to the end. So it has many 3 gates, input gate and output gate, and especially this forget gate. This 3 gate applies at each of the time points. So at each time point, the forget gate will decide what information from previous should be forgotten and what information should be added to the mainline, such that it can be kept for the later use. Please note that all of these gates are represented by, can be represented by a linear transform, and this linear transform parameters are all learned from a training process. And later, people have found that this long short-term memory model can be simplified. For example, this gated recurrent unit. And it only has 2 gates, update gate and reset gate. So it uses this update gate to decide what information should be updated for the mainline at each time point. So in principle, gated recurrent unit has less parameters than LSTM. So it's accordingly, it's faster, but it achieves comparable performance in many tasks as LSTM. And for recurrent neural networks, there are many of, not many, but there are 5 main different types of recurrent neural networks. The first is one-to-one. That means input has only one timestamp time point, and output also has only one time point. This would be just a simple network with only one neurons. And there could be a one-to-many problem. For example, image captioning, we want to use a short sentence to describe the content of the image. So the input could be just one image, and the output could be a sequence of words or a short sentence. There could be another example, could be a dictionary of word explanation. We want to use a short sentence to explain a word. And another type is many-to-one. For example, an example could be sentiment analysis. So like if we want to classify a review of product, the review could be a short sentence, could be a paragraph of text, and the classification could be just a positive or negative of the review. And there could be another type is many-to-many, but with identical lengths. So that means input and output have identical lengths. A typical example could be name tag identification. For example, we have a sentence and we want to find out which words in this sentence correspond to name. So basically, we need to output also a sequence of Boolean values for each word. The output could be either true or false, indicating if this word is a name or not. And there's another type, which is many-to-many, but the input and output have different lengths. This is actually the most widely used type of recurrent neural network. So I will explain it later in detail. And then let's see what can recurrent neural networks do. So recurrent neural networks are widely used in prediction. Time series prediction, for example, weather forecast, for example, stock forecasting. And it has also been widely used in language modeling, like machine translation, speech recognition, document analysis. And with them, it has been used in search engine and conversational UI. Because when we are talking about, sometime we want to talk about a customer online. No, not to talk to a customer, talk to a service online. In the beginning, it often answered by a chatbot. And also image or video captioning, this often used together with convolution neural networks for deriving image or video features. And it could also be used in music analysis and so on and so forth. Now let's talk about this the many-to-many type of recurrent neural network. The input and output have different lengths. So for this type of problem, we often use encode-decode architecture. So this problem also can be called a sequence-to-sequence, seq-to-seq. Let's take like these two examples. First is machine translation. For example, if we want to translate what did you do today in English into Norwegian, hva gjorde du I dag? So we can see that these two sentences have different lengths. The English sentence has 5 words, but Norwegian sentence only has 4 words. So we could not use a one-to-one correspondence to translate this sentence. And also, like for weather forecast, if we want to forecast precipitation in the next 3 days, based on the previous 7 days. So that is also 2 different lengths of input and output. It's not possible to use one-to-one correspondence prediction. In order to handle this problem, we use this called encode-decode architecture, but based on recurrent neural network. So it mainly has 2 parts, encode and decode. And encode is also a stack of recurrent neural networks. And decode is also a stack of recurrent neural networks. Connecting encode and decode, we use this called encoded, or can also called context vector, to connect encode and decode. The encode vector or context vector is actually just a final hidden state from encode. That means a hidden state from different time steps up to the end, and from the final node, the hidden state will be conveyed in the encode vector, and that will be used in the decode to derive the output. So in this case, information from encode or from input is used in the decode to generate output. And however, the pure sequence-to-sequence model also suffers a problem that is a long-term dependency problem. So, for example, if something is very important in the beginning of the input, if it is important for the output, let's take the example of this one. What did you do in English word? And we want to translate it into what you do. So we can see that this word, water, which is more important than other words for the Norwegian word var. So that means when we are translate this sentence into Norwegian, or when we want to get this word var, we often need to put more attention on this English word, water. So this is also inspired by the attention mechanism that also occur in our brain. For example, when we are looking at something, or when we are looking at a wide range of vision field, due to the limited resource of our vision sensitivity, we often need to focus our attention on certain object of interest. So this idea has also been used in this encode-decode architecture. So that is encode-decode with attention. And then the context vector from all the inputs, but also take into account the attention that is derived from each of the input time point, and it will also be used to generate the output step by step. For example, when we are generating the Norwegian word var, we might use higher attention weights than from the word water than other words. Please note that all of these attention weights are all learned from a training process. It's not assigned by manually, but it's learned itself. So, however, this encode-decode with attention is still based on recurrent neural networks. So the encode is a stack of recurrent neural network, and decode is also a stack of recurrent neural network. Then let's have a look at property, or we also call it shortages of recurrent neural network. As we see that from the mechanism of recurrent neural network, it's a sequential processing. That means the operations need to be done step by step through all the time points. So that means it cannot be processed in parallel or when training a model, the model cannot be trained in parallel. And also, recurrent neural networks suffers a problem of information. The early information is retained through the past hidden state. So such that it's hard to capture long-term dependency, as we have already explained. And also, it's also hard to emphasize a certain part. For example, in these two sentences, the cat doesn't want to eat a cake because it's not hungry. So we know that it indicates a cat, but in this sentence, the cat doesn't want to eat a cake because it smells bad. So in this sentence, it means a cake. So it can indicate different things based on the context, but this information might be hard for recurrent neural network to hardware, even though adding attention mechanism partly helped. So in order to solve the problem, people have proposed another very powerful model, which is called transformer. So transformer is based on purely attention mechanism. So transformer is also use encoder-decoder architecture, as you can see from the right side. Sorry. It has encode and it also has decode. I should mention that a transformer was originally proposed for machine translation. Yeah. So the properties of transformer don't have recurrent neural networks. So it's purely based on attention. Therefore, it doesn't have this non-sequential architecture. So then it can also capture a long-term dependency based on some so-called multi-head attention. It captures information from different time points and capture the information through attention mechanism from any time point and its importance for the output. So with the multi-head attention mechanism architecture, the transformer architecture can be run in parallel, and also it can capture richer interpretation of the sequence at different scales. However, because transformer doesn't have this sequential architecture, so it cannot retain the position information, because we know that the recurrent neural network using a sequential architecture, so not to retain the position information. So in order for the transformer to retain the positional information, it has to embed the position information, and this position information called positional encoding that can be directly learned from a training process, or it can also be computed using some method, like in the original transformer paper, it used sine and cosine to do a positional encoding. Without positional encoding, then any, for example, a sentence with any orders or maybe disorder words can also produce the same result. So the position embedding should be used. And in principle, transformer is faster, but it's also more costly than recurrent neural network. So since that, a lot of works have been performed in order to efficiently use transformer. Transformer was proposed in 2017, and in the paper titled "Attention is All You Need." Actually, the attention architecture can also be stacked. For example, in the original paper, 6 encoders have been stacked and followed by a stack of 6 decoders for machine translation. This paper is another revolutionary work. It not only proposed a transformer model, it also created a naming style. After that, many papers have been published on the name of something is all you need, something is not all you need. For example, money is all you need. That's a title of a paper. And then what can transformer do? Of course, because transformer was originally proposed for machine translation, so it can be used in time series problems, especially natural language processing. And by using transformer in natural language processing, a general approach is to use semi-supervised learning. That is to use something called self-supervised pre-train to train a large language model. So the self-supervised pre-train could be, for example, if people randomly remove some words in a sentence and then ask the model to learn what words have been removed or are missing. Or people can also ask the model to predict the next sentence based on previous sentences. So in this case, we do not have to annotate data manually, but because we have a lot of existing text or documents there online, so we could use them to directly train the model. This is called self-supervised learning. And after the model have been pre-trained based on a lot of sample data, we could use a supervised fine-tune to fine-tune a pre-trained model for our specific target problems. In this case, we just need to manually annotate a few samples in order to fine-tune the model, because we assume that this pre-trained model has already captured essential information about language. And there are several different pre-trained language models based on transformer have been published, and we can freely use them. For example, BERT. BERT stands for bidirectional encoded representations from transformer. That was a product of Google. BERT has two different versions, BERT base and BERT large, with a different number of encoders and heads. BERT has been already pre-trained, and we can use them in our downstream tasks. And there are also models called generative pre-trained transformers, version 2 and version 3. That was published last year. Version GPT-3 has really a lot of parameters, but it also very good. And people said that the quality of text generated by GPT-3 is so high that is difficult to distinguish from that written by human. So that means GPT-3 can be used to write stories, news, and document. And when it writes news, and we can even not distinguish if this news is written by a machine, GPT-3, or it is written by a human reporter. And in addition to time series or natural language processing, what can transformer also do? Transformer can also be applied in computer vision tasks. The first work is probably for object detection. That was done by Facebook researchers. So image is first processed by convolution neural networks to generate image features. And then the features are fed into a transformer encoder and decoders to detect and localize objects. So that model still uses convolution neural networks. But in another work, vision transformer, that is for image recognition, convolution neural networks is not necessarily needed. So they also just divide the image into different patches. Each patch has 16 by 16 pixels, and then split the patches into transformers. So they also have found that with larger scale train, and transformer can compensate inductive bias that was introduced by like convolution neural networks, which is helpful for image analysis. But the authors have found that if we are using a larger scale trend, the transformer, even without its inductive bias, transformer can also achieve very good performance to capture information for image recognition. And since that, almost every computer vision task has a solution based on transformer. For example, in this year's CVPR conference, there are more than 40 papers using transformer in different computer vision tasks. And that I would like to briefly talk about a very interesting model, which is called a Generative Adversary Network, GAN. It's proposed in 2014. So GAN is actually, maybe you have heard about an app called Deepfake that can change your face to any other's face on the photo. So that is actually based on something called circle GAN. Circle GAN is also derived from the original GAN. In the original GAN, it has two models or two networks. One is called a generator G, and another is a discriminator D. So the generator is trying to generate image based on some distribution. In the paper, it could be just a random noise. So the output is the image, and the discriminator takes the input of the generated image and the real image, and the discriminator tries to distinguish which one is real and which one is fake. But the G tries to generate image as real as possible, such that the D cannot distinguish. And finally, all the ideal goal is to achieve something called Nash equilibrium, finally. That means the discriminator cannot distinguish if the image generated by G is real or fake. Then it can be used for G to generate some images. So when training, again, D is first trained to strengthen its capacity for distinguish, and then G is also trained to generate real images. Based on the original GAN, circle GAN had been proposed that can be used in deepfake and other applications. Circle GAN actually has two generators, and also like a star GAN that can, for example, transfer baby image and to generate how the baby will look like when he or she is old. And however, we have talked about convolution neural network, we have talked about attention, we have talked about transformer, but are they really needed? Actually, very recent, last month, there are several papers that have been published trying to revisit the use of multi-layer perception. We know that multi-layer perception, MLP, is a simplest architecture of neural networks. And people have found that maybe a pure MLP architecture can also be used in image recognition and also to achieve good performance in image recognition. So we start with MLP and we go to CNN, RN, and to transformer. But are we back to MLP again? But maybe simple is always beautiful. But we need to note that even for all MLP architecture, it requires a lot of data to train the model. So in order to train the model, we need a lot of power. And maybe data is king, power is king, and maybe money is all you need. Because in order to connect the data, in order to train the model, what we need is actually money. And also, please also note that no matter it's MLP or CNN or recurrent neural network or transform, they are all different type of representation method to represent information from the signals. So this is still representation learning. And finally, let's talk about how to apply deep learning in practical problems. So the general pipeline of machine learning solution, I would call it BPDM. First, you need to understand your business. For example, your customer requirement, your resources. Do you have an expert, machine learning expert, or you need to go to like Norwegian Cognitive Center, or you need to go to NOS for help? Or do you need, do you have your infrastructure, or what your budget is, what your platform is? Are you gonna deploy or apply your machine learning model on the cloud, or are you gonna apply it on edge devices? All of this will decide what kind of models, what kind of problems, and then you need to understand your problem. By understanding the problem, basically you need to answer two questions. Input, that is what you will give to a model, and output is what do you want from the model. So the problem will decide what type of model should be used and how to use. And then you need to understand your data. What data do you have, and what scale the data is? Do you have a lot of data, or do you only have a few data? And are there any pre-trained weights that you can apply transfer learning, or do you need to annotate your data, and what that quantity is? And do you need to clean the data? Actually, in most machine learning problems, people have to spend much of the effort on data processing, clean the data, pre-processing the data, and so on. And finally, you want to build a model. You need to develop the model, you need to train the model and evaluate the model, and deploy the model in production, and also you need to monitor the run of the model. So that is called BPDM. And then let's see how to build a model. In principle, in order to build a deep learning model, you need to first implement some bricks. Like if you want to start from scratch, then you need to define the graph. That is the architecture of your model. And for each node, you need to define the feed-forward computation. That means how to compute from the input and how to compute output from the input in order to do the feed-forward computation. And also in order to solve neural networks, you also need to compute a gradient. But fortunately, if you do not need to build a model from scratch, we can use some modern deep learning frameworks or libraries like TensorFlow, like PyTorch, and you just need to build different bricks that have already been proposed by the frameworks. Then with bricks, how to construct a model? Can we do it like constructing a Lego model? If possible, but there are no fixed answer, because a deep learning model can be dependent on your problem, depending on your data and your infrastructure. But here are some personal experience, but maybe they are trivial, maybe not. So I would, when I develop a deep learning model, I would first define evaluation criteria. And ideally, it could be a single criteria in order to evaluate if my model is good or not. And also, if you do not know how to build a good model, smarter suggestion is to follow architecture that have been published in papers, published in GitHub or whatever. And but there are also some basic rules for like convolution neural networks and recurrent neural networks. In CNNs, in earlier layers, it often has a big spatial resolution, but less depth. That means less amount of channels. But at later layers, it often has low resolution but deep channels. And as we already said, that for recurrent neural network, we do not want to use a very deep architecture. And another thing is to build a baseline model. So when should you, when you want to compare or evaluate your deep learning model, you want to compare your model with a baseline. And then what is a good model? So a good model is often in between a simple model. Simple model is like it has a shallow architecture. It has a narrow architecture with a less number of neurons. And a complex model often has a deep architecture with many nodes. And so a good model is between a simple model and complex model. But in practice, I often build, if I cannot get a good model in the beginning, I often build a complex model. Because if I only have a simple model, it often unfit my data. But unfitting the data means there could be two reasons for unfit. The one reason is, of course, the model is too simple. But another reason is that maybe is because of data. If the data is too random and if there's no pattern that can be represented, so the model can also unfit. So that means for unfitting, we have to analyze two reasons. But if my model can overfit my data, that at least means that my data have some patterns that can be represented by the model. Then, based on the complex model, we can try to reduce capacity in not to fit your model, or in not fit the data, not overfit. By reducing the capacity, we could use a dropout, we could use regularization, we could reduce the depth, reduce the width, and so on. And also the error analysis is very important. For example, bias and variance analysis to decide if your model is overfitting or not. And the bad case analysis is crucially important in practice. And also sometimes if we need to use humans to label, to annotate your data, then compare with a human level performance is also useful. And based on this, I often want to do a quick iteration because currently deep learning is still kind of empirical. There are some hyperparameters that need to be adjusted. So in order to adjust the hyperparameters, I need to do a lot of experiments. So that means if I want to do an experiment and get results, if that takes a week or even a month, then I never do that. So I often want my model to give my result within half day or a day or maximum a few days. Then I can do the quick iteration to adjust the different hyperparameters. And in some cases, we could also try neural architecture search, given that you have a problem, you have a searching space and searching strategies. And all right, so we have talked about MLP, convolution neural networks, recurrent neural networks, transformer, again, and so on. But deep learning is a really rapidly developing area. A lot of new models have been published. For example, Jeffrey Hinton has proposed this capture network and GLOM in order to overcome some intrinsic shortages of convolution neural networks in computer vision tasks, and also graph neural networks that can be used to represent general architectures of different problems. And don't forget that reinforcement learning, and people thought that can lead to something called artificial general intelligence in the future. So this is a really exciting but very fast developing area. Thank you for your attention, and I'd like to take some questions.
Thank you very much. Please put your questions into the chat. I have a couple of questions, and Jeremy, if you also turn on your camera. Jeremy Cook is also worked at Norse. When we know that a third of the most important skill sets in 2025 is absent today, according to World Economic Forum, and 95% of all customer interaction will be AI powered by 2025 from Gartner Group. How do you see that organization that has not started using AI? How do you suggest they will start with this to get the competitive advantage they need to compete in 2025?
Yeah, that's actually a very good but also very challenging problem. So as we say in the presentation, applying machine learning in practical problems are often problem dependent. So, but I would suggest almost all industrial companies to think about, is it possible to empower your business with AI? But by saying AI, we're not only talking about machine learning. So for AI, there are two important parts, hardware and software. Machine learning is just for software. So for hardware, you also need to think about your infrastructure, your platform. So you need to think about, but these are all, of course, dependent on your problem. So if you have infrastructure that can be adapted to AI, and for example, in order to do a lot of machine learning modeling, we need to have data, and the data need to be connected by like different sensors. And then in order to apply or deploy the machine learning model in real time, we often need the data measured in real time. So in this case, we also need to think about Internet of Things. And so by combining your hardware, your infrastructure, and your problem, then you can think about what kind of machine learning model can be used. And also depends on the problem. Deep learning might always be the natural choice. You could also think about classic machine learning methods because as we know that deep learning often requires a lot of data trained, and also this data, I know that in practice, the data can be very difficult to get, especially if we need a lot of data. And also most times, or maybe sometimes, the data quality might not be always reliable. So all of this, you need to think about in a systematic point of view. And also, in some cases, you also need to build your digital platform first, because you need to run your AI model, your machine learning model on some platform. In this case, you need to, another buzzword, digital twins might be used. So can you simulate your practical scenarios digitally? that's also important thing you need to think about. I'm not quite sure if I answered this question, but that's my thought about apply AI in practical industry.
I think, Yun-Yong, you put that very well indeed, and in a sense, stole some of my thunder, if you like. But I think the most important thing for companies to focus on without even thinking about AI is on their digitalization of their processes. So this can be, you touched on many of those things, or maybe all of them, which includes things like Internet of Things, and understanding your data, I think. Once you understand your data a bit more, then you can get to a point where you can either get help or make some decisions on what kind of analysis methods you want to use. This could be more conventional methods, or it could also be the application of AI. And then I think you will have success in the digitalization of your data pipeline, so to speak.
Jeremy, you have worked with several AI cases with different kind of companies. What are their struggles when you start working with them? What's the main issue when you entering a new project?
Well, I think this, I guess this is different in every case, but if you, in general terms, I think more or less what I touched upon just now, which is to have some understanding of the data in your business processes available. So, I mean, let's say some applications of big data are that you take all of your data and you throw it into something that's going to analyze it, and it analyzes the data without any knowledge. So that could be a trained neural network in some instances. But what really helps is to actually understand and filter out your data, almost as a manual process, so that as a human you understand what's important about your data. This actually helps you filter down what are the important aspects. So you know, if you want to, somebody gave a very good example the other day. I mean, you want to be able to distinguish between, let's say, two pictures. One is a picture of a dog, and the other one's a picture of the cat. But the reason the neural network learns that this picture A is a dog and picture B is a cat, because in picture A there's let's say a red ball, and in picture B there's a blue ball, and the neural network might focus on, you know, the red and the blue ball, and not actually on the animal that's in the image. So these are kinds of things that you actually need to have some common sense about, let's say. So I just would say have some insight into your data, and don't just trust luck.
Okay, thank you very much. Thank you, Yun-Yong. Then I thank everybody for attending, and especially Yun-Yong for doing this lecture for us. And I wish you a nice weekend.
Thank you. Thank you very much.
Bye.
Bye-bye.
Thank you, everybody. Bye.